Today we're going to look at logarithms. Logarithms are the inverse functions of exponential functions. So if you can think back a few lessons ago, we learned about these inverse functions, and that is where our domain and range are switched. And if we're looking at it graphically, it's reflected over that y equals x line. So kind of in a way, logarithms and exponential functions are very much related. They are just inverses. The logarithm base b of x is defined as log base b of x equals y. So that is how it is read, logarithm base b of x if and only if b raised to the y equals x. That last part we'll talk about later in our notes. I do have it graphed over here to the right. F of x equals log base b of x, and you can see that shape. Let's talk about our general form that I have below there. Y equals a times log base b, quantity of x minus h plus k. All of our transformations still apply to logarithms. So those transformations, up, down, left, right, all of those still apply here. So let's talk about it. A still shows us a reflection if it is negative. If it's negative, reflects over the x-axis. It also tells us stretch or compression. Log base b. Now b will have some sort of value for its base. And then our quantity x minus h. We've used h before. H will show us a left shift if it's negative, or a right shift if it's positive there, going opposite directions for those left and right inside values. And then k, you remember, goes up if it's positive, or down if it's negative. That's our up and down movement. Now, logarithms have a vertical asymptote. If you recall, exponential functions had horizontal. So I'm going to go ahead and add that to our parent graph over here to the right. Here is our vertical asymptote. And for this parent graph, it's at x equals 0. Going back to our definition here, logarithms have a vertical asymptote of x equals h. So that h value just above there, where we were talking about our transformations, you can also put that that is going to be your asymptote value. And then don't forget, of course, h has an opposite sign. So if in the parentheses it was x minus 3, our asymptote would be at positive 3. Let's talk about the features of our functions. We did this same kind of setup with our exponentials, but now we're looking at logarithms. So number one, f of x equals log base 2 of x plus 5. The function f of x is logarithmic. I can see that in my log. I can also see that it has that vertical asymptote, which we're going to do next. The logarithmic function with a vertical asymptote of x equals. So I wrote it above in pink. In order to define a vertical linear line, we write it as x equals that number, would create a vertical line because every point would have the same x value there. Similarly, with exponential, they were horizontal and we said y equals a number. So just vertical is x equals a number. On this example, number one, our vertical asymptote is at negative 5. So labeling here our asymptote, coming over here to put in x equals negative 5. The range of our function, remember those are your y values. Let's talk about that. How low does it go? How high does it go? So we're talking about how low does it go. I'm looking at that left arrow and it is going down, 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 and it is going to keep rising and rising. Our upper arrow on the right, it is slowly creeping up. Very so slightly, but if I had infinity, it would. So, and I've already put it on our notes, so it's going to be true for all of your logarithms. The range of your function is from negative infinity to positive infinity. Range will always be all real numbers. Is this graph increasing or decreasing? We're going to look at it from left to right, and I see that it is going up from left to right, so it's increasing. On the domain of, so domain is our x values. So let's think how far left to how far right does it go? So looking at my left arrow, it is running into -5 on the x-axis. It is not going any further on the x-axis. It's not going to -6, -7, -8, or anything like that. It is stopping from -5 and going how far to the right? Infinity. So we're talking about domain here. It went from -5 to infinity. Okay, left in behavior. So looking at that left arrow, that bottom one, the in behavior as x approaches, what is x approaching? Is it going out towards negative infinity, or is it stopping at a number? Stopping at a number, right? We just talked about x is not going to -6, -7, -8. It's stopping at -5. So as x approaches -5 closer and closer, the y value is going down, 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 down. So negative infinity is our left in behavior. The in behavior on the right side, where is x going? X is going out, 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 out towards infinity. And the y is, I said, is creeping up ever so slightly, but forever. So it's inching, inching, inching up towards infinity. So again, we've got some that are going to be the same for every logarithm problem that we look at. So let's try again. I just highlighted above the ones that are going to stay for every logarithm. Number 2, new logarithm function. It says f of x equals -2 log base 2 of x plus 8. So I know it's been reflected, it's been stretched, it's shifted left 8 things. So we've got a lot of transformations that happen there. This function is logarithmic. I can see the log there. I can also see it is flattening on that vertical asymptote. So let's put that in, logarithmic with a vertical asymptote of x equals, where is it at? -8. Of course, I just said it was shifted left 8 places, right? So our asymptote is at -8. The range of our function, same for every logarithm. Our y values, it's going low, 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 little bit over time, and high, high, high forever. So range, our y values, all real numbers from -infinity to +infinity. And it is increasing or decreasing. As I look from left to right, it is falling, decreasing. On the domain of, so we're talking x values, how far left does it go? It hits at -8, doesn't it? Let's not get our 8s and our infinities mixed up here. It's stopping. It's not going to -9, -10, -11. It is stopping on the x-axis at -8. And how far right does it go? Forever. -8 to infinity. Woo, that looks crazy with those infinity symbols. All right, let's talk in behavior. On the left side, so my left arrow is up here at the top, the left side. Where's x going? As x approaches what? That asymptote, right? My x on that left side is not going to go to -9, -10. It's stopping at -8. So as x approaches closer and closer to -8, it's going to keep just creeping closer to that -8 as it shoots up. The y value is shooting up towards positive infinity. Okay? Right in behavior. As x approaches, where's the x going? How far right is it going? It's going to keep shooting out to infinity. Our y is going where? It's slowly going down. Slowly, but it is going down to negative infinity. So look at those two problems. See how they compare? It looks like I am noticing our y values on our in behavior, they were going to positive or negative infinity. We also saw in our domain, they were running into our asymptote. So our asymptote could be on the other side. So don't always think it's the left in behavior. It could be right in behavior if we had a negative inside that reflected it over the y-axis as a transformation. Do you notice any other patterns? We had, our domain. Our domain ran into our asymptote, okay? Our asymptote value we also saw in our domain. So little couple things, features there. So identifying exponential versus logarithmic, and there are certain ones that are always the same here as well for logarithmic functions. Now, at the beginning of our notes, we said logarithms and exponential functions are inverse functions, and therefore we could use inverse operations to solve them. So let's dig a little bit deeper into these. Exponential form shows a base raised to an exponent equals the result, right? Like if I had a raised to the b, it equals c, whatever those numbers may be. Logarithmic form shows that the log of the result with a given base equals the exponent. We've got a typo there. Let's fix that. Okay. Logarithmic form shows that the log of the result, so that c value, the log of c with that same base, the original base from the exponent form is also logarithmic form, equals the exponent. Let me do exponent in just a different color. B equals b. Okay. Let me show you with real numbers, right? So let's take number 3 and write it in logarithmic form. We had 100 is equal to 10 squared. True statement, no big deal. So I'm going to change it to a logarithmic form. The log base 10 in our exponential form, 10 was our base with the exponent of 2, right? So a base is still a base between exponential and logarithmic. Log base 10 of 100 equals 2. In logarithmic form, it shows the log with the result with a base is equal to the exponent. It's equal to the exponent. Yes. Let's try again. Number 4, 3 raised to the 4th equals 81. Log, same base, log base 3 of 81, the log of the result equals the exponent, 4. Let me try one more time, see if you can see how this is coming together. Number 5, 5 squared equals 25. So log base 5 of 25 equals 2. So again, exponential form, logarithmic form, they are very much related. We will use them as inverse operations to help us solve. Let's just scoot right back down to page 2 of our notes, and we're going to go backwards. Let's take the logarithmic form and put it as exponential. So number 6, we have log base 3 of 9 equals 2. What would that look like in exponent form? The base is still our base, raised to my exponent of 2 equals 9. And that's still a true statement. 3 squared equals 9. Just like when you go and solve a logarithm, log base 3 of 9 equals 2. When we solve or simplify a logarithm, it tells us the exponent. Number 7, log base 9 of 729 equals 3. Let's put it in exponent form. We have the base was 9, so it's still my base. 9 cubed, 9 raised to the 3rd, is equal to 729. And number 8, log base 4 of 1 equals 0. This seems really odd. Let's rewrite it. 4 raised to the 0 equals 1. This still might feel funny for some of y'all. Guys, anything raised to the 0 exponent is equal to 1. You can check it on your calculator. I can explain to you deeper how that happens, but anything raised to the 0 power is equal to 1 in our exponents. Now let's evaluate our logarithm. In number 9, we have log base 5 of 125. What would that equal? Now remember, logarithmic form, when we solve it or simplify it, it tells us the exponent. So let's just put it in exponential form to see if we can kind of make some connections. The base was 5. Raised to the what in exponent form would equal 125. Do you know the exponent? 5 raised to the what would be 125? If you don't, you can use your calculator. So on my calculator page, I'm going to hit the log button, which is in blue from the 10 to the x button. So hitting control and then that 10 to the x, and look how beautifully our Inspires typed this up. We have an open box for our base 5. We've got an open box for our number 125, enter. It is 3. 5 cubed is equal to 125. So let's say log base 5 of 125 is equal to 3 is my answer. Number 10, log base 6 of 216. What would be the exponent? What would be the answer here? So if I had 6 raised to the what gives me 216 is what we're asking ourselves. Is it 2? 6 squared is 36. Is it 3? I'm not sure. Let's grab that calculator. Control 10 to the x is going to give me that log. We had base 6 of 216 is 3, another cubed. So log base 6 of 216 is equal to 3. Number 11, log base 2 of 2 to the 8th. Let's see. 2 raised to the what? What is the exponent? Is equal to 2 to the 8th. Okay. Wait, this notation looked really complicated, but when I rewrote it into exponential form, I can see what they need, right? Log base 2 raised to 2 to the 8th of 2 to the 8th is equal to 8. That missing exponent is 8. So let's see what the calculator does. Control for my log, we had log base 2 of 2 raised to the 8th is 8. Yes, perfect. Now the base 10 logarithm, so far we've had base 5, base 6, base 2. If it has a base of 10, it's called a common logarithm and is written as log x with the base 10 implied. So if you have log base 10 of x, we just leave it as log x. And everyone knows if there's not a base shown, it's implied that it's 10. Also, the number e is an irrational number, just like pi. The first time you were ever introduced to pi and pi is a number, what? Same thing here. E is also a number. It's an irrational number equal to 2.71828182845. Yes, you get the point. Now, if we have a base e logarithm, we call it a natural logarithm, and we write it as ln of x. So if I have log base e of x, it is called a natural logarithm, and you're going to hate me for this, but it is true. Natural logarithms we represent as ln of e to the x, just showing that it is actually just ln of x. So if you're using a natural logarithm, you're representing it with ln. Everyone knows the base there is e. Nothing else is used. The expressions log base 10 of x and log x mean the same thing, as do ln base e x and ln x, which is what we were just talking about a moment ago. So everyone knows those are the same, and everyone knows those are the same. So let's evaluate some problems using that information, the natural logs, the common logarithm. So in number 12, we have log of 1,000. It didn't show a base, so we understand it to be a base of 10. In other words, 10 raised to the what would equal 1,000. So when I evaluate log of 1,000, I know that is 3. 10 to the third, 10 times 10 times 10 is 1,000. In number 13, we have ln, or the natural log, of e to the fifth. Remember, natural log, or ln, is using a base of e, and then we have e to the fifth. So let's use exponential form. The base e, what exponent would give us our result, or the e to the fifth? It's going to be 5. ln, or natural log, of e to the fifth is just 5, because when I showed it in exponential form, the base equal to the result, I can see I'm missing that 5 as my exponent. In number 14, we have log of the fifth root of 1,000. There's not a base written, so it's understood 10. We could rewrite this as log base 10 of 10 raised to the 3/5. How did I do that? I'm going to show you on the calculator, but 10 cubed is 1,000, and you know from your rational exponents that fifth, that denominator, was the number I got from my root. So then when I write it as exponent, the base raised to what exponent gives me 10 to the 3/5? It is 3/5. So final answer, the log of the fifth root of 1,000 is equal to 3/5. Let's grab the calculator and let me show you. So let's do a log. You can leave your base blank or you can put in a 10. It does not matter. A fifth root of 1,000. 0.6, you can do menu number, approximate to a fraction, 3/5. But I wanted to show you how that works out. If you feel comfortable with that, run with it. If you don't, you can refer to your calculator. Number 15 is a little bit easier, but using the same concepts, we've got ln, the fourth root of e to the third. Remember, an ln is a natural log with an understood base of e. So we have e raised to the what gives us e raised to the, change this to a rational exponent, 3/4 to show that fourth root. And you can see how we're getting our answer there. Final answer, natural log, the fourth root of e to the third is equal just to that 3/4. Number 16, some more interesting exponent rules. So we have base 7 raised to the what would give us 1/49. If you're very confident in your exponent rules, you might pick up on this one really quick. Everything's been shifted to the denominator, like as though it was equal to 1/7 squared. What moves us into a denominator? A negative exponent. So our final answer is going to be -2. Log base 7, 1/49 is equal to -2. Again, I can show you on the calculator how that comes together. Control our log base 7. I'm going to use the fraction boxes here. 1/49 equals -2. Just applying our exponent rules there with our logarithms. In number 17, we have the natural log of 1/e to the fifth. This looks insane. So remember, it has an understood base of e. E raised to the what would equal 1/e to the fifth. This kind of piggybacks over to our last problem. So I somehow moved into the denominator. What made me do that? A negative exponent. So we have ln of 1/e to the fifth is going to be -5 is our missing exponent there from that exponential form. Let's check it on the calculator. You do have a natural log button, control, and right next to it, you see that ln. I'm going to use those fraction boxes with control divide, and we have 1/. Your E button is right there, highlighted for you, raised to the fifth, and enter. You can see that -5. So wanted to illustrate how those exponent rules work. If you're feeling confident doing those by hand, rock it out, but you can always check with your calculator. So that is logarithms, again, the inverse of exponential functions. We talked about the features that exponential functions had that horizontal asymptote. Our logarithms now have a vertical asymptote. We looked at the domain, range, and end behavior with those functions as well. The transformations apply here as well. And then we worked on actually looking at those forms, exponential and logarithmic forms, rewriting back and forth to see how they are related. Again, we are going to use them as inverse operations to solve. And we also talked about the common logarithm and natural logarithms. You can check a lot of this on your calculator. Guys, let me know if you have questions, and I'll see you in class. Have a great day.